Hello everyone, my name is Angela Brown and I will be presenting and discussing my Lab 3 report for Physics 2212. The purpose of Lab 3 is to measure the distance dependence of the magnetic field due to a bar magnet and compare it to the predicted value for the on and off axis Biot-Savart's law derivations. The principles and assumptions used throughout the lab are Biot-Savart's on and off axis derivation, dipole assumption, and Earth's magnetic field. The setup began with placing a meter stick and phone on the floor. I downloaded the Tesla Meter app to measure the magnetic field due to a permanent dipole magnet. The app does measure in microtesla, so I had to convert to teslas when plugging in my data. For every value, I multiplied it by 10 to the negative sixth. Using the app, I rotated my phone till the x component was 0, indicating that we were aligned with the Earth's north and south. I placed the meter stick along the bottom edge of my phone, which was the east-west, and placed the magnet along the same direction. Since I am located here in Atlanta, Georgia, the magnetic field is 94 microteslas. Now it is time to find my phone's magnetometer chip and measure the distance dependency. I found my phone's magnetometer sensor by finding the maxes and mins of particular components, X and Y, using Tesla meter, and my phone was oriented parallel to the meter stick. I marked this location on my phone. All measurements will be taken using this location on my phone. Next, to find the distance dependency expressed in the formula on the screen, I found the distance from the magnet to the sensor that produced a magnetic field with an x component of the given various magnitudes. While taking these measurements, my phone was oriented perpendicular to the meter stick. I recorded the distance and the x component on the spreadsheet. The experiment was repeated 2 more times for each magnitude. The distance we were calculating is the r within the equation, and the goal was to calculate n. The pre-made Excel sheet graphed out the natural log of the x component of the magnetic field versus the natural log of the distance r. The slope is the value n that we desire, and the y-intercept is natural log of k. Using the data from the graph, I was able to calculate mu by replacing b bar with the magnetic dipole axis equation, where the distance is larger than the separation of the dipole. We assume that r is equal to 1, and now we have an equation only with the variables k and mu. Since the natural log k is the y-intercept on the graph, I was able to create an equation. To cancel out the natural log, both sides were placed to the power of e, which enabled us to calculate the value of k. Then I plugged k into the previous equation and calculated mu. The next course of action was to measure the off-axis magnetic field. I used the same setup from the previous calculation, including orientation of my device. I found the distance in which B net equaled 100 microteslas on my phone. I recorded the distance as d perp and the y component on the spreadsheet. The y component is the Earth's magnetic field. Next, I placed a new meter stick at d perp and perpendicular to the meter stick already on the ground. Not changing the orientation of my phone, I moved it across the new meter stick at a distance d perp. At the location, I recorded the x, y, and z components displayed on my app. For the y component, I had to take into account Earth's magnetic field, which I found when we first found d perp. I had to add the two y components to get the corrected value. The x, new y, and z is the magnetic field at 45 degrees at distance d. What I observed throughout the lab was when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. Also, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. For the coding part of the lab, I began by plugging in the new mu I found previously and a random distance. Then I created the function dipole B to calculate the magnetic field of the magnet at various different observation locations. Within the function, I found r hat and plugged it into the equation given in Lab B, which will be shown below. I created the magnetic field at various locations on the axis and perpendicular to the magnet. The arrows were created by calculating the r, then using the dipole B function. To find the magnetic field at 45 degrees, the r vector for x and y components, rd perp, which was calculated in the experiment. Then I ran it through the function. In conclusion, when comparing the magnetic field at 45 degrees in the experiment versus the code, the noticeable difference is that the experimental value has a z component. The reason that the z component within the code is 0 is because it does not take into account Earth's magnetic field. Time for the final concept questions. For the first question, if the orientation of the meter stick was north-south instead of east-west, we wouldn't know the magnetic field we were measuring. We would have to evaluate and take into account the Earth's magnetic field in the x and y component. For the second question, by adding a second magnet to the first one, I would expect for the magnetic fields that I measured to be twice their value.